Thank you, Chairman. And what I'm going to do is to just introduce a little bit of work on foraminifera, which I'm aware that I'm probably in a minority of people in the room who really work on foraminifera. But I'll try and explain why it's important in the acidification debate, based on a mixture of the fossil and modern analogues. So here we have a peaceful scene in the late Maastrichtian. Well, it's peaceful if a mosasaur isn't going to eat you. I should say that this fanciful picture with seagrass meadows is now actually true, because we found 3 seagrass meadows extending over 100 meters across the Maastricht quarries. And it raises an interesting question of, did grass evolve in the oceans rather than the land? I'll leave that one with you. But of course, we know mosasaurs fed on ammonites. There's a few ammonites there with teeth marks in them, which are pretty well mosasaurs. And one of the things that, of course, anyone working on the KPG wants to know is, when and why did the ammonites go extinct? Well, of course, most micropaleontologists, when they process samples, look at all sorts of odds and ends. Sometimes there really are odds. These are, of course, the very juvenile protoconchs of ammonites. And, of course, you can follow these up to the KPG boundary, and they go. That's it. So you lose these protoconchs. So whether you want to blame the mosasaurs, whether you want to blame ocean acidification in surface waters for dissolving the very fragile aragonitic protoconchs of ammonites, we can have that debate. Well, starting off on just about the one section Terry didn't mention was Denmark. And of course, the Danish section is the one I started looking at, the KPG boundary. The interesting thing is that, of course, if you forget your basic geology, you don't understand why some of the structures appear on one part of the coast and not on the other. Just think of 2 dimensions, 3 dimensions, structures disappear. I wish our students could remember that occasionally. But when you go to the northern end of Stevensklint, what you find is a boundary section which is fairly expanded. And when we look at this and process it, you can see that you've got nice chalk succession below. You've got the limonitic layer right at the base, which is effectively, I suppose some people would call the ejecta horizon, although actual ejecta is not in it. Some person once published a picture of all the spheres which turned out to be tasmanitid spores. They clearly weren't a palynologist. But when you look at this section, you can think of what you're looking at. And I've probably processed more chalk samples than most, so I've got a pretty good idea of what a beaten up chalk sample looks like. And of course, here you can see the nanofossils, the planktic forams, ostracods, and all the other things that go to make up the chalk. The one thing, of course, that isn't carbonate are the organic walled plankton, dinoflagellates. And of course, when you look at the boundary section, which I've cut and extract here, all these chalky, or nearly all these chalky things disappear at the boundary, and what you're left with is a black mudstone which is full of dinoflagellate cysts. Not a monospecific assemblage that Stefan Hultberg described. He actually oxidized all his materials, so therefore he didn't have anything. And he therefore came to the conclusion that it was a freshwater succession that, well, never mind. The palynologists in the audience will know what happens when you oxidize your samples too badly. Well, let's jump across the infamous pond for a moment and look at the Brazos River. We've been looking at this to try and understand what the benthic foraminifera, as well as the planktic, are doing. And what we've done is looked at a whole range of localities stretching down the river and into some of the parallel creeks that many of you will have read about. This is one of the sections. It's interesting that Helen Plummer, who, like a good Texas Geological Survey operative, would have walked every riverbank, every creek in Texas as part of her work, said that there were two small anticlines in this section. Well, this is what she was looking at, this curved surface there, but actually it's this surface here. It's not an anticline, it's a depositional feature. And when we worked with Tom Yancey, what we found, and we found again the same thing in Alabama and Mississippi, is that the uppermost Maastrichtian had been carved into a series of positive areas and negative areas. And one of the things you find up on the top of these features there is a shell pavement. And these things were actually positive features. And when you plot these out, they are at right angles to the direction to Chicxulub. So we can see the eroded surface quite easily. So this is the succession you find in that section that's pictured in your abstract volume. What we have are the Maastrichtian mudstones below. We have a spherular bed, then what's been called the event bed. And the interesting thing is above that we return to a mudstone succession, which we can now show the timing of this. And what we see, and somebody mentioned recovery earlier, in a paper recently, which is referenced in the abstract volume, we suggested the initial recovery after the KPG was begun 30,000 years after the event and was virtually, in terms of the micro-paleontology, over by about 85,000 years, which for the fifth biggest extinction event in the geological record is horrendously quick, or at least our little component of it is. Well, when we look at the benthic foraminifera, and Helen Plummer actually said she was shocked when she visited this section in Texas, that she could actually see the small benthic forams with her naked eye. And you can. They're on the bedding surfaces. These are not larger foraminifera, they're smaller ones. And what we find is that they didn't notice the boundary. It's virtually the same assemblage. It's virtually the same ecological mixture above and below the boundary. And the preservation is the same above and below the boundary. So these benthic foraminifera didn't see what was happening. Now, when we look at what we would expect to find in acidification, if you go into the Mediterranean at Ischia, there's a wonderful location where carbon dioxide's bubbling through the sediment, and you can measure the pH and you can look at the foraminifera. And when you do that, you see that as the pH goes down from 8.17 to 7.8 to 7.6, your calcareous assemblage changes completely into an agglutinated assemblage. The calcareous things can't cope with a pH of 7.6. Now, this is a static environment. This is settling down to that, and the diversity drops as well, and the composition drops. So we know what the benthic foraminifera should do if they're suffering acidification. Why? Without going into the details, to create a calcareous test, the foraminifera have to raise their internal pH to about 9. So if you reduce the external pH to about 7.6, 7.5, they cannot produce a calcareous test. End of story. When you go to an area like the Gulf of California, Gulf of Cortez, where there's methane and carbon dioxide vents coming out onto the sea floor, what you find is if you collect a living foraminiferid, in other words, one that we know had protoplasm in it when it was collected, what you see are beautifully pristine pores. Preservation's fantastic. And yet the pH is measured at about 7.6, 7.5. However, when they die, what happens is that their pores start to be corroded away. So we can recognize post-mortem changes as well as actually in situ changes. So where does that leave us? Well, when we look at our little section of the Brazos River downstream from the bridge over it that some of you will have visited, we can see these benthic foraminifera. They are not even suffering depositional, post-mortem changes. So what we expect to see happening is that the acidification, if it's there, and the proloculi and the protoconchs, the ammonites have gone, so there might have been. What we see is a whole series of changes, but the benthic foraminifera show no acidification. But the planktics have disappeared, the nanofossils have suffered greatly, and when you look at some of the changes, what we see are a whole series of changes within the nanofossil community, and there is a horrendous amount of reworking, as what you'd expect, following what might have been a tsunami event. There's Campanian and Maastrichtian erosion and reworking, and my co-author, Matt Hampton, when he saw some of the specimens and photographs of the nanofossils that were in situ in the Maastrichtian, and others which are now within the Paleocene, he said it was like them going through an acid bath. They're completely etched. I could show you hundreds of photographs, but as there's not many nanofossil specialists here, that might be rather tedious and I don't have time. But the message is that in situ on the sea floor, the Maastrichtian nanofossils were fine. Only the ones that have been reworked into the Paleocene have been etched by the acid bath. So what we've got is, and I'm sorry about a storyboard here, I should animate it, but my computer skills long since died. Here's our mudstones, there's an ashfall deposit, here goes the tsunami, then a reworked spherule bed, then the event sandstones, and then the Paleocene succession. And the acidification event is literally over within about 30 to 35,000 years into the Paleocene. Now, there is a model that Plymouth Marine Lab told me about, and I can't even understand the equations, let alone the maths, that ocean mixing and shelf mixing would have mixed any surface water acidification within 30,000 years, just by natural mixing, not doing anything to it. So what I think we're looking at is an acidification event which hits the ammonites, or the ammonite protoconchs, the nanofossils, the planktic foraminifera, other calcareous organisms, but not the benthic foraminifera that were in the Texas successions, living in approximately 75 meters water depth. So they weren't affected by that. And what we do is we can then correlate our little model and fit the Brazos succession against our Danish and other successions. So where does that leave us? Well, it leaves me out of time because I've got an orange light in front of me. But when you look at the record, we're pretty certain we've got acidification at the KPG. We've got acidification at the Paleocene-Eocene thermal maximum, but that is a totally different type of acidification. It's deep water acidification, not surface water. When you go to the Triassic-Jurassic, those of you that remember, I made a comment about it. If you look at the paper I co-authored on the benthic foraminifera across the Triassic-Jurassic boundary, they're a ragonitic foraminifera. And again, we can see the recovery because once you get past the acidification event, and there it is actually etching the dead foraminifera. Their pores are being widened, as I showed you in that other photograph. And then gradually the calcareous assemblage of benthic foraminifera come in, and the story goes on. But there is an event there. It's rather detailed foraminifera work, and I'll leave that out. Thank you.
Okay, thanks, Malcolm. One quick question.
Hi, those the reworked Maastrichtian nanofossils that are showing the etching. So do you think they were just being resuspended and etched in surface waters in the Paleogene? Is that what you're saying?
I think, well, what Matt Hampton found was that there was the whole of the Maastrichtian and part of the Campanian flora mixed up with these nanofossils. And to get that sort of distribution, I think they're being picked up and they're hitting this surface water acidification event. I can't think of any other way of transporting them and not getting them through that environment. As I say, the benthic foraminifera, and there are reworked benthic foraminifera across the Maastrichtian boundary, but they're much bigger items and they're not bouncing up into the surface waters, so they're not affected. And that's why I think that model might work.